So I'd like to keep this informal. If you have any questions at any point, please don't be afraid to interrupt me. Just chime on in. So I'm going over the yet another kernel launcher. That's what YAKL stands for, C++ Portability Library. So I have to imagine a lot of you are quite familiar with C++ portability, and there's probably a good number of you who are not that familiar. So I'm going to try to strike a balance, but I'm going to edge towards those who are less familiar. Just to acknowledge that OLCF and ECP projects have both contributed funding to the development of YAKL. So I'll start off first. What is Portable C++? I want to emphasize that Portable C++, it's a library. It is not a separate language. It's not a language extension like some of these directive-based things are. It is just pure raw C++ as far as most of the code is concerned. And so it is well supported by nearly all existing compilers. It uses the same information that you already give in your non-parallelized code, especially if you're using something like OpenMP, Target Offload, or OpenACC. All the information that you're providing for them is sufficient for portable C++ implementations as well. One of the interesting things about C++ is it gives you the ability, unlike Fortran, to pass a section of code as an object to other functions. And so what you can do with that is take, say, some function inside a set of nested loops. You can wrap it in, typically we would wrap it in something called a lambda, and then pass it as a parameter to some other function that can then launch that code in parallel over a series of indices on any kind of backend that you want. So you could do it in CUDA for NVIDIA GPUs, HIP for AMD, and SYCL for Intel, and so on. There's a lot of flexibility in what you can do with that. So we can't do this in Fortran, at least not with any current standards, because I don't know of a way to encapsulate code as an object in Fortran, but in C++ we can do that. The nice thing about this is a single source code will run on many different hardware backends. I do not claim that this approach is, quote, performance portable. That is a very complicated definition. And the way that I personally approach the idea of performance and portability is to get decent performance on a lot of different architectures rather than micro-optimizing for a single architecture. I think that's a better way for a productive project to get their simulations done. Portable C++ libraries typically come with other features like multi-dimensional arrays, a way to handle race conditions where multiple parallel threads are trying to access the same data at the same time, typically in a read-write manner, and ways to handle data between two different memory spaces. The complication when we're using GPUs, and I should have prefaced, a lot of this exists because we're having to port codes to use graphics cards and other accelerator devices where the accelerator has its own high-speed memory, whereas the host has a slower memory, and these live in completely different spaces. So you have to transfer data back and forth, which leads to a lot of complexity that we're not used to. So again, this is hodgepodging slides from different presentations, so sorry for the repeated information, but to see it visually, if we were to look at a Fortran code, this information in green here is defining the threading. So we would be slapping these loops together into a single level of parallelism, and we'll distribute the body of the loop among those threads. And so if we want to say, a kernel would just be the code inside the loop body. And the threading that the kernel is run over is described by the loops around that code. So all the information that we're used to using in code, it's the same amount of information that we need for C++. If we were to look at this as a kernel with YAKL, the syntax admittedly is a little bizarre if you're used to Fortran. And I've tried my best to minimize the amount of syntax change or syntax shock that you have moving from one context to another, but some of it is inevitable. This idea of taking a bunch of different loops and putting it into a single data structure. Cocos has to do the exact same thing. Their syntax is a little more verbose than YAKL's, but it's describing exactly the same thing. And then we have this Lambda, like I mentioned earlier. If you don't know what that is, it's totally fine. One way to approach this is to just, treat it somewhat like as a black box and take a look at these commented loops and take a look at the bounds in the Lambda and just match up, the pieces of information until you get used to the what's actually going on behind the scenes. And the code inside the loop stays exactly the same in every way. There are no changes necessary there. So it's not true 100%, but to a large extent, the biggest syntax shock, so to speak, is going to be in describing the parallelism, the looping. Again, codes can pass, C++ can pass code as an object, and that's the reason that C++ is useful in this regard, to running the same code on multiple different backends. So yet another kernel launcher. If you're interested in learning more about it, you can follow this link here, and I will pop these slides onto that Confluence page after this presentation. I've tried my best to make it well documented and as approachable as possible for people who are not used to C++. And I do have an article written for people used to OpenACC and OpenMP target offload to kind of soften the transition to something like C++, because a lot of us are not used to C++. Currently, YAKL supports CUDA, HIP, SYCL, CPU, OpenMP threading, and OpenMP target offload. Although I will admit that target offload is in progress, there are a number of issues that make that particular backend a little bit difficult. In fact, we're waiting on some compiler support for some atomic directives to use the hardware. But you can use NVIDIA, AMD, and Intel GPUs today with full functionality. The NVIDIA and AMD backends perform quite well in some of the tests that I've run. If you have questions about that, please come ask me individually. I know this is being placed on YouTube, so I'm hesitant to give some firm performance numbers about AMD GPUs in particular, because the early testbed system, a lot of that information we just want to run by the Center of Excellence before we distribute that publicly. But please come talk to me if you have any questions. The performance has matched the aggregate bandwidth improvements on every machine I've run on, which is a sign that the ports using YAKL are doing their job appropriately. It started as a stopgap while HIP was not yet supported by Cocos a few years ago. That was, of course, quickly remedied by Cocos. It works great on AMD GPUs. But that was kind of the beginnings of YAKL. I needed to start playing around on AMD GPUs, and I couldn't wait for the existing more functional frameworks like Cocos and Raja to support it first. I really wanted to get some experience ahead of time. But as I was going through that effort, it turned out that it was quite useful in porting some of our larger Fortran codes. When you have 5, 10, 20,000 lines of code to port over, it's very difficult to have to permute all of the array indices and to trace all of the integer arithmetic, subtracting the lower bounds of the Fortran arrays off. It might seem like it's not a big deal, but when you have that kind of level of code, it becomes very cumbersome to have to handle all of that. So I thought, why not just create some functionality in the multidimensional arrays that allows them to behave as much as possible like Fortran arrays. The other thing I want to mention is YAKL is very small. It's only 8,000 lines of code. Something like Cocos is, hundreds of thousands of lines of code. So I don't think YAKL should be perceived as some sort of drop-in replacement for Raja and these other more functional C++ frameworks. It has an emphasis on simplicity, simple syntax readability, and a niche application for porting Fortran codes quickly over to C++. It was developed with a very small amount of effort, less than a fifth of an FTE spread over a few years. So this is not some massive code that we're introducing into E3SM. It's still quite small. YAKL, like a lot of the other portability frameworks, has a parallel for function that will launch kernels over a series of threads, which should be thought of just like a tightly nested loop that we put OpenACC directives on, for instance. It has multidimensional arrays that are both static and dynamic. So you could think of the static ones as automatic arrays in Fortran, and the dynamic are the ones that you actually call allocate on. And you can do these in C style or Fortran style. And when I say Fortran style, I'm talking about column major ordering and lower bounds that are arbitrary and default to 1 and basic array slicing. We have functions to move data between host and GPU memory spaces. There is an efficient non-blocking pool allocator, which has turned out to be one of the key performance mechanisms for the codes I've ported over. A lot of our Fortran codes do frequent allocations and deallocations of the memory, which it's not only expensive at Fortran, but when we do this on, say, a CUDA, an NVIDIA GPU in CUDA, those allocations are extremely expensive. So having a pool allocator run transparently in the background allows you to create arrays anywhere you want and destroy them anywhere you want with no penalty to the runtime. Not any penalty that you'll notice because it always overlaps with kernel runtime. We have ways to handle race conditions like every portability framework, like atomic operations and reduction operators. I don't have scans in there yet, but I'm happy to put them in there if the need arises for a global scan operation. We have synchronization for asynchronous work so that you can, for instance, wait until all the kernels are done before you send data over MPI or something like that. And there are a growing number of Fortran intrinsics like min, val, sum, and pack. A lot of these were developed when porting the RRTMGP code over to C++ because they make quite a bit of use of some of these routines. So it's just easier just to create them and to keep the code looking as similar as possible to the original. And there are some automated timers. So if you label your parallel fours, it will automatically put timers around them if you put the right macro in your compile line. And the output looks very similar to GPTL, and you can override the timers to use GPTL. So it can work with our existing models, and it has I/O through netcdf and pnetcdf if you want to use that, especially for debugging. Again, interrupt me at any point if you have questions. So to show an example of code going from Fortran to YAKL, here's a kernel that would give you the maximum stable time step of a shallow water model, for instance. So anybody familiar with Fortran can pretty much understand what's going on. We have an assumed shape array for these 3 variables that we're pulling in, height, u, and v. I'm curious, can you see my mouse when I move it around?
Yes.
Okay, awesome. So we got to grab the size of the arrays using the size function. We want to initialize the time step to something large because we're going to take the minimum. So all of these functions that you see here are also represented in YAKL. So if we move over, this top section that you see here, this, using and type def statements, this would not actually be in the user level code. What you'll typically do is hide this stuff out in a header file somewhere so that you don't have to see all this really ugly syntax that you're not used to if you're coding in Fortran. You'll have to kind of understand what these things mean, but oftentimes you can have somebody who's more familiar with C++ create some of these convenient type defs for you. And when you actually run the code, like you see here, you'll just be using the types that you defined, and you don't have to deal with these templated expressions and namespaces. So in this case, we're going to use a Fortran-style array, Fortran-style bounds. They'll be allocated on the GPU and memory device. And when we come down to the function itself, now it really starts to look a lot more like the original Fortran. So we can grab the sizes of the arrays just like we do in Fortran. That code doesn't change at all. Epsilon doesn't change at all. When we declare an array, that looks a little different than you're used to in Fortran. We have to give it a label like you see here. But this will allocate an array for you of size nx by ny. And nx would be the fastest varying dimension because it's a Fortran-style array, so it's column major. So all that stays the same. When we launch the do loops with a parallel for function, I like to pass a label. You should do this in Cocos as well whenever you launch a parallel for, because it allows the C++ portability library to do things like automated tagging in, say, an NVProf profile on the NVIDIA GPU, or if you want CPU timings, it can wrap these things in timers for you, and you don't actually have to insert timers yourself. It'll do it automatically. So we're going to say we have two bounds, and we're going to have ny be the outer loop and nx be the inner loop. And it will loop from 1 to ny and 1 to nx because it's Fortran-style. And we're going to have the integers that associated with those loops be j and I, just like we have above here. And when we actually look at the computations, everything stays exactly like it was before. The array indexing looks exactly like Fortran. And finally, when the kernel's done, we're going to calculate the minimum of all the time steps, which is how we get the maximum stable time step for the shallow water model. So from what you've seen here, this is kind of as bad as the syntax change gets. So you can see there are some changes. I don't see any way around them necessarily, but most of the code can stay exactly the same. So if you're porting thousands of lines of code, it makes it a lot easier because there's a lot of tedious work that you don't have to deal with. So why would we bother with C++ in the first place? Again, it decreases your reliance on compilers. So because you can pass the code manually yourself to well-supported backends like CUDA and HIP and SYCL, it gives you a little more power as a developer, and you have to rely less on the compiler doing exactly what you want it to do and not understanding the complexities of what's going on under the hood. C is always the first implementation that any vendor develops, and C++ quickly after that. This is critical if something has to work day one. So if, in my case, I'm on the hook to ensure that the E3SM MMF code works day one on Frontier. That's my job as a liaison for the E3SM project under ECP and under Insight as well. So I want to use the technology that I know will work on day one. Fortran has been known to lag C implementation in terms of robustness by years or decades, honestly. It depends on the features that you use, of course. And some, situations, Fortran doesn't actually have an implementation like HIP or SYCL or something like that. You would just have to use OpenACC or OpenMP directives. And in our experience, well, not everyone has this experience, so please don't take this as everyone's experience. But OpenACC and OpenMP target offload have had a tendency to be somewhat buggy when you use modern features of Fortran. And the larger the code, it tends to be, the more these bugs tend to express. And when you try to, say, give a reproducer in a smaller code, it can be very difficult to do. We've had this honestly since I've been working on GPU within E3SM for 10 years. When it was called CESM. So again, this is one of the reasons that we're looking to move to C++. Is it does tend to give better and not better, more robust behavior in terms of reduced numbers of bugs. But there are codes even within E3SM that are working today quite well with OpenACC. So don't take this as some sort of catch-all statement for everyone's experience. The codes that have been developed with YAKL so far are the system for atmospheric modeling that we ported from Fortran, the portable atmospheric model, which is the new cloud resolving model for the MMF, the ECP side of E3SM. The RRTMGP radiation code we ported over, and we just found it easier to jump to different backends from the C++ side. There's a ADER We Know Finite Volume, or AWFL, unfortunate acronym for the shallow water model, that has been ported over. And then there's a mini app called MiniWeather. I'll do a pause real quick. If you're interested in learning more about parallel programming, getting your hands dirty with a fairly easy code to work with, it's only maybe, at most 100 lines of code that you actually care about, and the file is only 400 lines long. You can code in Fortran or C with MiniWeather, and you can get access to a lot of different parallelism strategies, including MPI, OpenMP target offload, OpenMP CPU threading, OpenACC, and C++ portability, as well as Fortran based. So you can actually use the Fortran standard to do parallel do with MiniWeather as well. So hopefully that's helpful if anybody wants to take a look and learn more about getting your hands dirty with parallel programming. And there's some preliminary investigations into using YAKL for Impasse Ocean. They're just kind of taking a look at some of the kernels and seeing what works best for them. And it may or may not be YAKL in the end, but it is one of the options that's being looked at. Before I open up to any questions, I do also want to say YAKL is not for everybody. So again, YAKL's design is meant to help developers have to think of as little as possible when they are porting a code from Fortran to C++, or honestly just developing a new code from C++. PAM, the portable atmospheric model, is a new development. And I'm using YAKL for it because it reduces what the developer is able to put in there in terms of complexity, and it kind of forces the developer in some ways to write code that's a little bit more readable. But say for the Screen project, for instance, they have design targets where the YAKL would probably not be appropriate for them. They really wanted to use hierarchical parallelism, for instance, where you have an inner and outer loop that you launch within some parallel unit, like a streaming multiprocessor, then an outer loop that you distribute over them. In that case, YAKL is not appropriate for that sort of thing. Cocos is the better option. So if you're wondering, should I use something like YAKL? Should I use something like Cocos? You can talk to me or any of the folks at Sandia working with Cocos, and we can help you make that decision. If you really want a lot, if you want a substantial amount of complexity in your code and you want a lot more control over individual bells and whistles of performance, you may want to use Cocos instead. If you're looking to port a lot of code and you want it to work fairly well on all architectures, and you don't really want to be in the driver's seat of a lot of those small level decisions, could be that YAKL is a good choice for that particular case. So it's not for everyone, but it is helpful for the cases that don't need a lot of complexity. So if a single level of parallelism is good for you, and you only need to know about two memory spaces, a host and a device, for instance, it could be that YAKL is a good design target. There are a lot of limitations, and they are all documented on the website. So here is the wiki page for YAKL on GitHub. This has been developed by myself, Isaac Lingos at Oak Ridge, Abhishek at Argonne, who's done a ton of work on the SQL backend in particular, and Mark Barrell at Oak Ridge as well. And there's a whole series of documentation, from introduction and overview, how do I compile with it, and all the way down here. I encourage you, if you're interested, take a look at some of the documentation. Again, I've tried to make it as well documented and readable as possible. If you want to look at the YAKL code, I have made it very easy to follow the best I can. There is very little abstraction. You don't have to go searching for the code, and I've tried my best to comment all throughout, even YAKL itself, to help guide you through what's actually going on in the back end and why are we making some of the decisions that we make. Two notable things that are going to be included in YAKL over the next month or two. If you want to launch work in multiple streams, you can do that. It is added complexity, which is why I'm somewhat hesitant, but some people have expressed a desire for this. So that will be in there soon. And hierarchical parallelism, I am investigating that as to whether that complexity is worth adding into this framework, or if we should just say use the Cocos parallel dispatch instead of YAKL in that case. I want to keep this simple and tuned exactly to the applications that it's useful for, rather than implementing exactly the same functionality of every C++ portability library out there. So that's always a hard design decision to make. But with that, we got a few minutes left. So if you have any questions, please ask away.